Now that you know about exponents and roots, in this section we will be simplifying roots. And more specifically, we'll be simplifying square roots. Now, what do we mean by simplifying? So let me just show you a few expressions or the few perfect squares that we know. So, for example, 1, square root of 1 equals 1. Square root of 4 equals 2. Square root of 9 equals 3. Square root of 16 equals 4. Square root of 25 equals 5. Square root of 36 equals 6. Square root of 49 equals 7. Square root of 64 equals 8. Square root of 81 equals 9. And square root of 100 equals 10. Okay, so these numbers that are inside are called perfect squares, perfect square numbers. Because when you take the square root of these, you get a whole number, a nice whole number. These are called perfect squares. And you get these perfect square numbers by squaring whole numbers. So, for example, to get this number, you just do 1 squared. To get the second one, you just do 2 squared. This is 3 squared, 4 squared, etc. 5 squared, 6 squared. And you can get any perfect square numbers just by squaring a number. And you can get the square roots of perfect square numbers. And that's just going to be a whole number. Now, what happens if we have to take the square root of a number that is not a perfect square? So, for example, square root of 24. 24 is not a perfect square. Right? 25 is a perfect square, but 24 is not a perfect square. So when we're taking the square root of 24, we can't really get a nice whole number for this to equal to. So that's why we are simplifying this expression into an expression that it's easier to read. And before we actually simplify this, I would like to introduce you to a property of roots. So, for example, if I'm taking the square root of two numbers that are being multiplied, so let's say 4 times 9, I can distribute the square root to both of these numbers like this. Square root of 4 times square root of 9. And we did something very similar to this when we were dividing, or we were doing fractions, square roots of fractions. We can distribute the square root to the numerator and then to the denominator. Right? We can do the same thing when two numbers are being multiplied like this. That is going to equal 2 times 3, which equals 6. And you can kind of check that you did this correctly, because instead of evaluating these separately like this, you can multiply these first. 4 times 9 is going to be 36, and square root of 36 is going to be 6. So you'll get the same answer even after you distribute the square root. Now notice you can't do this. This is just extra information. You can't do this when you're adding two numbers together. You can't make that into square root of 4 plus square root of 9. This is not okay. But this is okay. Okay, so using this property of roots, let's try and simplify square root of 24. Now, 24 itself is not a perfect square. But inside 24, is there a perfect square inside 24? So by perfect square, again, I mean the numbers I've circled in green here. And you'll notice that inside 24, there's a 4, right? 4 is a perfect square. There's a 4 and a 6, right? So you can rewrite the square root of 24 as the square root of 4 times 6. And the reason we're rewriting it like this is because we can take the square root of 4. Now this is going to equal, using our property over here, that's going to equal the square root of 4 times the square root of 6. But we can do the square root of 4, right? So that's going to equal 2 times the square root of 6. So this is our simplified answer, 2 times the square root of 6. The square root of 24 is going to equal 2 times the square root of 6. Let's try another one. Say we're trying to find the square root of 32. Square root of 32. Is there a perfect square number inside 32? And there's actually a couple. So you can either write this as 4 times 8. 4 is a perfect square number. Or you can write this as 16 times 2. 16 is a perfect square number. Right? Let's use both of these. It's actually better to use this one, and I'll show you why. But both of these are going to give you the same answer. So rewriting it as square root of 4 times 8, that's going to equal the square root of 4 times the square root of 8. And the square root of 4 is 2 times the square root of 8. Now the reason I said 16 times 2 is better is because here, inside 8, there's another perfect square, which is 4. So you can do the same step again. So that's going to be 2 times square root of 4 times 2. And then again, that's going to be another square root of 4 here, which is going to be 2. So 2 times the square root of 2. And the answer, I'll write the answer up here. The answer is going to be 4 times the square root of 2. Now you'll get the same answer with 16 and 2. So square root of 16 times 2 is going to be square root of 16 times the square root of 2. Square root of 16 is 4, and then you're left with square root of 2. Right? You get the same answer, but you had to do another extra step when you used this, because inside 8 there was another perfect square number. But either way, you're going to get 4 times the square root of 2. So as seen in this example, it's better to factor out, or to factor it into the biggest square number possible. Right? 16 was better to work with. Notice the number of steps that we took using 16, it was much less than the steps we took for 4 and 8. So if you can factor this with the biggest square number or perfect square possible, then it should be the easiest way. Let's try one last example. All right. Let's have the square root of 150. Okay, so inside here, is there a perfect square number? And if it's not easy to see right away, you can always try using prime factors. So if you do a prime factor for this, that's 10 times 15. That is 2 times 5. That is 3 times 5. You'll notice that there are 2 5s contained in here. Right? There are 2 5s inside 150, which means that there's a 25 inside 150. Right? And 25 is a perfect square number. So if you're not sure about what kind of perfect square numbers are inside our number, then you can use the prime factors And if there are two of the same numbers, then that means that that number squared is inside that number. So we can divide 150 into 25. So once you get 25, the rest is 2 and 3, right? So that's going to be 2 and 3, so 6. So this is 2 5s, and this is 2 and 3. Then you can rewrite this as square root of 25 times the square root of 6. And square root of 25 is 5. And we can't simplify square root of 6, so that just becomes square root of 6. So this would be our answer. Okay, I've said this is the last example, but I'll need to do one more example. Apologies. The reason I'm doing this example is to deal with a case when we have a whole number out front already. So let's say we have like this. Right? Let's say we have this, and we need to simplify this. 7 times the square root of 50. So obviously, when you have something like this, a whole number times a root of something, just do the root part first, and then you can deal with the whole number later. So let's just focus on the square root of 50 for now. Is there a perfect square number inside 50? Now some of you might automatically realize that that's 25 times 2, right? But for those of you who don't, or who are harder to see that, you can again use prime factors. 5 times 10, and that is 5 times 2. So again, there are 2 5s inside here, which means there's going to be a 25 inside here. So that's going to be 25 times 2. And then that's the square root of 25 times the square root of 2. Square root of 25 is 5, and then we have a square root of 2. Now we need to consider the whole number that was in the front, and you just simply multiply that whole number to the whole number that we have here. Okay, so 7 times 5 is going to be 35, and then square root of 2. Okay, so it's not really hard. As long as you can simplify the root, then having a whole number in the front isn't that much of a problem. You can just simply multiply the whole number to the whole number that you get after simplifying the root.